Okay. Okay, so last time we talked about Noetherian modules and so on. So mostly Noetherian modules, and we saw some examples and some key results. So let's just recall that module M is Noetherian. So there were many three equivalent definitions, but so one of them was that all its submodules should be finitely generated. And then we observed that submodules of a Noetherian module and quotient modules of a Noetherian module are also Noetherian. And partial converse is a converse of this is also true. So you can phrase it this way. So this was I think one of you made this observation that if M be let M be an R module, N contained in M be Noetherian R submodule such that M mod N is Noetherian, then M is Noetherian. So the proof is similar to the proof you can use the same technique which we used in this theorem that a finitely generated R module over a Noetherian ring is Noetherian. Yeah. So this was the main result which we proved last time. R is a Noetherian ring, then M is Noetherian if it is finitely generated. And the other direction is more or less is by definition that if M is Noetherian, then it is automatically finitely generated. And a consequence of these results is that, so basically we are interested in finitely generated modules, or when a module is finitely generated. Yeah, and Noetherian is sort of concept defined so that we can work with it. Yeah, so it's slightly stronger, and so for Noetherian rings, finitely generated R modules and Noetherian modules are the same thing. So in particular, we get that if R is Noetherian and M is a finitely generated R module, then any submodule of M is finitely generated. Okay. So of course, this is not true for non-Noetherian ring. Yeah. So maybe. So first of all, why is this true? Because if M is finitely generated R module over a Noetherian ring, then by this theorem which we proved, M is a Noetherian R module, and then its submodule is going to be Noetherian and hence finitely generated. Yeah, so it automatically follows immediately from the two previous results mentioned. Yeah. And what's an example of a example where this fails? So you start with any non-Noetherian ring, for instance. So take R to be, let's say, polynomial ring in infinitely many variables. So that's an example of a non-Noetherian ring. And M to be R itself. Then of course M is finitely generated. M is generated by 1. M is generated by 1R as an R module. M is same as R, right? So it contains 1R as an R module. Yeah. So every element you can write of M, you can write it as R times 1R. Okay. So it can it is finitely generated, but if you look at the submodule or here the ideal x1, x2, so on, this I this ideal I contained in M is not finitely generated R module. So it's a submodule. So submodules of M are precisely ideals of R, because M is R. And of course, if you take a non-finitely generated ideal, then it won't be finitely generated as an R module. Okay. Okay, so now today we'll learn about localization of modules. So this is also like Noetherian modules were sort of like Noetherian rings. It was some sort of a generalization of Noetherian rings in some analog of Noetherian property in modules. Localization of R modules is also similarly an analog of localization of rings, but in module setup. Yeah. So the definitions are very parallel, and we'll see the definition and some examples. Yeah. So it goes more or less in the same way as localization of rings. Yeah. So we'll have to define things somewhat similar way. So let R be a commutative ring and S be a multiplicative set in R. So multiplicative subset of R. What does that mean? S is a multiplicative subset of R.
So closed under multiplication and contains one.
Yeah, so it contains one and is closed under multiplication. Yeah. And M be an R module. Then one can define a relation on the set S cross M. So remember there, then we had S cross R, and we were trying to define an equivalence relation to define localization of rings. So you replace R by M, yeah, and that is pretty much what you do throughout. Okay, so on S cross M, you define an equivalence similar to S cross R. So you say that S1 comma M1 is equivalent to S2 comma M2 if there exists S in S such that S1 M2 minus S2 M1 is 0 times this element S on the left. So this is so M is an R module, yeah. So S1 times M2 is going to be an element of M, yeah. So it's an element of, this is the scalar multiplication, and similarly S2 times M1 is a scalar multiplication. So maybe I should put a dot here, yeah, and to denote this a scalar multiplication. Yeah. And if I don't put anything, that means it's a ring multiplication within the ring. So this should be the 0 element of the module. Okay. And then so if you define this relation, then the first thing is that this is an equivalence relation. That's what we showed in the case of rings as well. So let M over S denote the equivalence class S comma of the pair S comma M for S comma M in S cross M, and the set of all equivalence classes you denote it by S inverse M. So S inverse M is S cross M modulo the equivalence relation. That means set of all equivalence classes. Then one can define M1, declare this plus circle to be M1 over S1 plus M2 over S2 to be S2 M1 plus S1 M2 over S1 S2. So trying to define a binary operator on S inverse M. So, so the first claim is that, so the second, after this equivalence relation, the second claim is that this is a well-defined binary operator on S inverse M. So well-defined is what we have to check. And of course, it takes two guys in S inverse M and produces one guy in S inverse M. So it is indeed a binary operator. And then there is the map sending R over S to M, R over S comma M over S prime, these two equivalence classes, one in S inverse R and the other in S inverse M, to Rm over S prime. Yeah. So so this map is well defined. Is the third. So maybe I should label these things. So one, maybe this is the second claim. This is the third claim. Okay. And then finally, S inverse M is a S inverse R module via sigma as the scalar multiplication. And in particular, so maybe let's put this as 5. So in particular, S inverse M is an R module. Yeah. So it has both R module structure and S inverse R module structure. So why is it an R module? Because any S inverse R module is also an R module, because we have a ring homomorphism from R to S inverse. Okay. Any questions? Also we have a map from M to S inverse M, which is going to be I linear. So maybe let's call this 6. So the map let's call this phi from M to S inverse M, sending M to M over 1. Yeah, this makes sense because 1 is in S, is in R linear map. Okay, so S inverse M is an R module, M is an R module, so it makes sense to say that this is R. Okay, so so the action of R on S inverse M is clear, right? So R goes to R over 1 in S inverse R, and then R over 1 will send M over S prime to Rm over S prime. Yeah. So what happens is R sends S, R times S M over S goes to Rm over S. That is the scalar multiplication of R on its inverse. Yeah. Okay, so let's see. I mean the proofs are more or less same as the ring case, but let's just so this maybe those who remember the proof it will be a review, but anyway, it's a good idea to see it again. So think of it as a review if you already remember it, but if you don't remember it, another opportunity to learn. Okay, so proof. So first, maybe I'll check only a few things. So maybe this equivalence relation is okay. So yeah, so I don't know what all I should check. So things. Yeah, so maybe this is an equivalence is a reflexive and symmetric is immediate. Is reflexive and symmetric is immediate. Because of course S over M is related to S over M, because the one in the middle is going to be 0, and symmetric because you just change the sign. Yeah, reflexive and symmetric is trivial, follows trivially. And for transitivity, let's say S1 M1 is related to S2 M2, and S2 M2 is related to S3 M3. Then we want to say S1 M1 is related to S3 M3. So you just write it down. So maybe I'll use, so there exists U in S and V in S, such that U times S1 M2 minus S2 M1 is 0 in M, and V times S2 M3 minus S3 M2 is 0 of M, 0 in M. And from here you can you multiply this by V, the first equation by V and the second equation by U, and take the difference. Yeah. So let's call this 1. Let's call this 2. Then V1 minus U2 gives UV, so the middle guy will get cancelled, or not minus but maybe plus. Yeah, then you get UV S1 M2 minus minus S3 S1.
So shouldn't it be S3V and S1U?
Sorry, 1 second. S1, S2 M3 and S3 M2. This is okay. Yeah, say that again.
So shouldn't it be like S1V, sorry, S3V1 plus S1U?
Yeah, so this is not, and this formula is not working. Let me just see. So I want to cancel out this M2 term, right? I would just want M2, and so what are you saying?
S3V times the first term and S1U times the second term. That way the coefficients of M2 will become equal.
Okay, so S3V times the first one, yeah, then M2 will get cancelled out, yeah, plus S1 S3V, yeah, S1 is here, so S1U times the second one, yeah. So it's I'm pretty sure it's the same thing which we did for rings. S1U for the second one. Yeah, so then now if you add, then hopefully it will get cancelled out. So what you get is S3U V S1 M2 minus S3 U V S2 M1 plus S1 U V S2 M S1 U V S2 God sometimes. S1, are you there? Hello? Yeah.
Yes, sir.
Okay. S1 UV S2 M3 minus S1 UV S3 M2 is 0. That's what we get. And then hopefully something, this M2 term will get cancelled out. Yeah. So this and this, the first and the last term are same. So you cancel it out and you factor out whatever you can factor out. Yeah. So in this case, you can factor out S2UV. Yeah. So you factor out S2UV times S1M3 minus S3M1 equals 0. Now which implies, since S is closed under multiplication, S2UV belongs to S2UV belongs to S. So this implies that S1M1 is equivalent to S3 and M3. Is related to S3M3. So this is indeed equivalence relation. So I don't know, maybe the plus we already had checked. So it's that it is well defined, yeah. So maybe and scalar multiplication. So maybe 2 and 3 same as the ring case. You know, you can in fact copy down the same proof with M replaced by R essentially. M1, M2 replaced by R1, R2, and in the second one M replaced by R prime. Yeah, and you'll get the same proof. Okay, so maybe I'll skip this one. So maybe we'll just check that S inverse M is indeed an S inverse R module via this operation sigma, via this scalar multiplication sigma, and then 5 and 6 also we will. So I already said why it is true, so maybe write it down also. For 4, S inverse M. So we have to check that it's an abelian group. So S inverse M is an abelian group, and then we have to check the 4 axioms. So for that, first thing we have to check is that S inverse M is an abelian group. So so the elements of S inverse M are equivalence classes like this. So 0 over 1, we want to say that 0 over 1 is the additive identity. So note 0 over 1 plus M over S by definition is S times 0 plus 1 dot M over S, which is S times, so anything times the 0 element of the module is 0, and 1 dot M is M. So that is one of the module axioms. So the numerator is M and the denominator is S. Yeah? So 0 over 1 is the additive identity, or the identity of this group. And so we have to check associative and commutative and inverses. So okay, so I don't know. Commutative is straightforward from the definition, because in the this ordinary plus is commutative, so this is going to be commutative, and associative. So maybe so. Okay, so I don't know. Associative. I don't know how much I should do, but associative. So S1 M1 plus S2 M2 that's S3 M3. By definition, this is sorry, I've written all upside down. So SIs are elements of capital S and MIs are elements of the module. M1 over S1 plus M2 over S2 plus M3 over S3 as S1 S2 S2 M1 plus S1 M2, and then you have to do N3 S3, and that is same as S1 S2 S3 and S3 S2 M1 plus S3 S1 M2 minus S1 S2 M3. Yeah, so this is what you get if you add it in this order, and if you add it in the other order, M1 over S1 plus M2 over S2 plus M3 over S3, then but you'll get somewhat similar thing. Yeah, or maybe something, sorry, plus, no minus here. Yeah. And so you get M1 over S1 plus S3 M2 plus S2 M3 over S2 S3 and S1 S2 S3 and you get S2 S3. So S2 S3 M1 plus S1 S3 M2 plus S1 S2 M3. Yeah, which is same as the top guy. Yeah, so these two are equal. So you get associativity. Similarly, you can write or see that is commutative. So you and the negative exists. So minus M over S plus M over S is 0 over S square, which of course is same as 0 over 1. Because the difference is 0. Yeah. So 0 over 1 and 0 over S are all same. So you get so this is indeed a abelian group. S inverse M is an abelian group, and then you have to check all the module axioms. So so 1 over 1 dot M over 1. So this is by definition 1 M over 1 1. Sorry, 1 1 1, which is M over 1. And so you have to check R over S plus R1 over S1 plus R2 over S2 times M over S. The scalar multiplication via sigma is this guy. Is same as so by definition of sigma. So this is the definition. Yeah, numerator and denominator you have to multiply. So for that you first have to add it. So it's S1 S2 S2 R1 plus S1 R2 dot M over S is same as S2 R1 M plus S1 R2 M over S1 S2 S. And I'm pretty sure if you do the other way, so maybe yeah, so I'll just compute the other way and show that this is same. R1 over S1 dot M over S plus R2 over S2 dot M over S is same as, by definition, this is R1M over S1S plus R2M over S2S. And if you multiply them, you get S1, S2, S squared, and R1, S2, and maybe I'll put S here, M. So I mean the ring is commutative, yeah. So if okay, maybe it's not that important that the ring is commutative. So let me just write it in a. But we are doing only for commutative ring, yeah. Yeah. So let me not worry about it. S2S R1M plus S1S R2M is what we get in the numerator, and this so as we can factor it out, so what we get is S2 R1M plus S1 R2M times S, and S times S1 S2S, yeah. And then you can show that this fraction is equal to the fraction. So this these two are in the same equivalence class. Yeah. So that will tell you that. So this is same as this, which tells you that these two are equal. Okay. So and similarly the other distributive law. Yeah. Similarly, I'll just say what one has to check. So R over S times M1 over S1 plus M2 over S2. Similarly, check RM1 over S. I don't want to check it, but I just want to say that you can check that you get this plus R over S M2 over S2. Okay, so what does that tell us? And then finally, so this, and then this one is more easy. R1 over S1 dot R2 over S2. M over S is same as R1 R2 over S1 S2 R1 R2 M over S1 S2S, which of course is same as R1 over S1 times R2 over S2. This multiplication is in the ring times this is the scalar multiplication. Yeah. So so this is what makes it into a this is what makes it into a S inverse M into an R module, S inverse R module. Okay, and then what was number 5? Is an S inverse R. So in particular, S inverse R is an R mod. S inverse M is also an R module. So in particular, okay. So recall R to S inverse R, sending R to R over 1 is a ring homomorphism. Hence S inverse M is an R module, and in fact we know it explicitly. So R dot M over S is going to be R over 1 dot M over S, which by definition is Rm over S. Yeah. So this is the scalar multiplication. So so S inverse M is not just an is an R module as well, and the R module structure of is given by this S inverse via this map, if you like. Okay, and the map finally the map phi from M to S inverse M. I'm going to M over 1 is our linear map is our linear. So to check that, we have to check that it's a group homomorphism and it preserves and it behaves well with scalar multiplication. So phi of M1 plus M2 by definition is M1 plus M2 over 1. Yeah, but this is also M1 over 1 plus M2 over 1 by definition of addition in this S inverse M, yeah, which is phi of M1 plus phi of M2. Yeah, so phi is a group homomorphism. And then the next thing you have to check is it behaves well with respect to scalar multiplication. That's also okay. So for R in R and M over S in S inverse M and M over S in S inverse M. So here also this is so for all M1, M2 in M. This is what happens, and thus and M over S in S inverse M. Phi of no, not M. Sorry. So what we have to check is for M R in R and M in M. Phi of R dot M by definition is Rm over 1, and this is same as so what is the this is how the scalar multiplication R action on S inverse M is. So this is so from here, like here. So this is by star. This is same as R dot M over 1. Yeah, which is R times phi of M, because phi of M is precisely M over 1. Yeah, so phi is R module homomorphism. Okay, so this completes the proof of this thing, which is not difficult, but just tedious. Yeah, you just have to write many things. Okay, any questions? Okay, so if you're still awake, let me go to some examples. Yeah, so so how do you compute localization of some modules? So we will we'll do one example which will be sort of instructive and give you an idea about what you get. So so let's take R to be, maybe I'll make it fatter. Let's take R to be the ring Z. Yeah, and M to be the Z module. I don't know why it's not moving. Maybe Z, one copy of Z cross. So if I take M to be R itself, then of course S inverse M is same as S inverse R, because the definition was just replace R by M. Yeah. So if M happens to be R, then of course S inverse R M is equal to S inverse R, and then you are saying that S inverse R is an S inverse R module. Yeah, so maybe that should have been example 1. So we'll come to this, but first observation is M equals R, then S inverse M equals S inverse R. I mean, this is, I don't know, tautology. S inverse M is S inverse R as an S inverse R module. S inverse R is a ring, so it is an S inverse R module as well. And of course, we also know that S inverse R is an R module as well. Yeah. So everything fits into it. Yeah. Now, secondly, if in this example R equals Z, and let's take M to be Z cross maybe Z mod 15Z. Yeah. So this is our module, and take S to be some multiplicative set. So maybe part A is S equals V space. Part A is S equals, maybe we take 1, 3, 3 square, and so on. So let's call this S3. B is, so we have taken one of the factors. S5 would be somewhat similar answer, so let's not do that, but maybe S15 is 1, 3, 1, 15, 15 square, and so on. So it should give you something else. If we take S to be 1 or minus 1, then of course you shouldn't get anything interesting, I think. Yeah, so let's not worry about that, but maybe what if we take C, S to be all non-zero, guys. Yeah. So S to be Z minus 0. Okay. So these are the three cases, and we want to compute S inverse M. So what will happen in this? What is S3 inverse M? So first we'll have to guess what happens. Yeah. So so if it was just Z, then of course we would get S3Z. Yeah. So S3 inverse Z. Yeah. and somehow this is product, and everything is component wise. So S3Z should remain. S3 inverse Z should be there. So that is Z adjoin 1 over 3. But what happens to the other guy? So what happens to this? What happens to the other factor is what we are looking for. Yeah. So yeah.
So can we say that a non-trivial zero divisor is becoming a unit over here? So
Yeah. So I mean, it's not a ring. We shouldn't think of Z mod 15 as a ring, but yeah. So what happens is we are inverting 3. Yeah. So what you will get here is that um, yeah. So what you'll get here is okay. Maybe first I'll make claim is that this is going to be Z mod 5. Yeah. Okay. And the claim is that S15 inverse M is isomorphic to, no, this is not right. S3 is Z adjoin 1 over 3. Yeah, so this should be, okay, so maybe I'll have to think about it a little bit. So these are Z1 over 3 module. Yeah. So Z1 over 3. So what happens to 3? Yeah. So 5 times 3 is 0, but 3 is a unit, so 5 must become 0. So this should be Z mod 3Z. Okay. Okay, and this should be just Z1 over 15. The second factor, the whole of second factor should become 0, and this should S inverse M should be just Q. Okay. So you should get rationals. So let's try to see why this is true. Yeah. So maybe we'll see the first one and then take a break and then do the second and third one. Yeah. So the first one is the most complicated one because we're getting half of what I mean. It's we're inverting something but not inverting everything. So so let's see why that is true. So yeah. So second. No, I think this should be isomorphic to Z mod 5Z. This is okay. So it should be isomorphic to, sorry, Z mod 5Z. So 5 will become 0, but which means it's Z mod 5Z. 3 is a unit. So let's try to see this. Yeah. So S3 inverse of M. So consists of yeah. So maybe I should have just done Z mod 15Z. So to simplify notation. So let's just try to compute this, and then we will prove that for product it just splits that way. Yeah. So just to simplify the notation, Z mod 15. So Z mod 15 is a Z module, and we want to compute S3 inverse of Z mod 15Z. Yeah. So this this is going to be um, um, uh, yeah. So let's just write it down. Class of A over so in the denominator we can put 1, 3, 3 square or whatever, yeah. So 3 power n. 15 is an element of Z mod 15, and n is some number greater or equal to 0. Okay, so this is what, as I said, this looks like. But there are some, so these equivalence classes, so there is some relation among these equivalence classes is what I want to say here. So yeah, so what is the equal relation? So
like over here, if n is greater than equal to 2, that's the same as the lowercase, because in 15, like multiplying by 3 is the same as multiplying by 3 power n. Some extent.
Yeah. So
I mean, not the normal multiplication. Multiplying something by 3 to get a 0 is the same as multiplying by 3 power n to get a 0. That's what I mean. Because there is only one factor of 3 in 15.
Yeah. So I want to say some. So I want to make some statements. So I have to say that there are only 5 elements here. Yeah. So this. So what is okay. So how do I do this? One second. So 1 over 15. So maybe if we decide what this is, then we'll be more or less done. Yeah. So so I think this should be okay. So 1 over 3 power n should be same as 1 over 3 power n prime. So if we show this, then more or less we are done. But is this true?
So if we take a 5z,
yeah. So this is okay. Yeah. So yeah. So this is indeed true. So note that for n prime. So as long as the denominator has one copy of n, yeah. So n prime, no. So this is not, I can't multiply by 5.
I was saying, as in, if we have a 5 over instead of 1, if we have 5k or something like that over there, we can show that it's equal to 0.
Yeah, that is true. But what happens to 1 over 3 power n?
1 over 3 power n, so it's don't have much information over because it varies with n.
Yeah, but the ring should have the module should have only 5 elements.
Yes, sir. So that's what we can show, as in it's not trivial, but we can show that it's a group. It's not trivial, and it has less like it has less than equal to 5 elements, and some element is order 5 or something like that. Then we can verify it's 7.
Yeah, yeah. So, but yeah. So, which element? My guess was that one will have the order 5. Yeah. Uh, hmm. So 1 over 3 power n and 1 over 3 power n prime should be same, but it's not turning out to be. Yeah, but each of them has order. So this has order 5. Yeah, that is clear. So, but how do you show that these? So this has order 5 is okay, but how do you show that any two such elements are same?
So they need not be same over here.
No, but then it will have many elements, which I thought is not true. So,
So
mm,
just in this case, if we multiply by 3 power k above, just to equate the denominators in both of them,
mhm.
it's pretty much possible that 1 is equal to 3 power something, and when that 3 power something is not equal to 1.
Yeah, let's just try to see what do you get. So 3 power n prime um, mm, minus minus 3 power n. Yeah, so this need not be, no matter what you multiply it, may not equal 0. Yeah.
Yes, sir.
So this equality may not hold, but but some sort of equal. So okay, this kind of equality may not, but it's still it should have only 5 elements. Yeah. So how do I show that there are only 5 elements?
Sir, could you just verify once whether this works? I was thinking of proving it like this. First of all, I show that it has at least 5 elements. Just using this order, that 1 by 3, that element has, it's not 0. I verify it's not hard to verify it's not 0 because it's coming 1, 3 power n is equal to 0
One
or
over
something.
one maybe. Yeah. So this is okay. This has order 5.
Yes, sir.
Order 5. I mean, this is the um, so this is not going to be 0, and you can show that 2 over 1 is not 0 and 3 over 1 is not 0 in the same way.
Yes,
Up to 4 over 1 is not 0.
yes, sir.
Uh, but how do you show that everything has to be? Yeah, so maybe one has to use some arithmetic. Yeah. Okay. So so note that 1 over 3, 1 over 1, 2 over 1, 3 over 1, 4 over 1, and 0 over 1 are, they all belong to S3 inverse Z mod 5Z. Okay. So these are S3 inverse Z mod 15Z, sorry. And you can check that they are all different. Yeah. So because so for instance 1 over 1 and 2 over 1, so for them to be same, there should be an element some power of 3 such that that times 1 is 0 in Z, which that times is 0 in Z mod 15, but that can't happen. Yeah. So and no multiple of 3 and some number different from 5, less than 5 can be a multiple of 15. Yeah. So they are all distinct and elements of this thing. And then I want to show that any number, so and of course 5 over 1 is 5 over 1 is same as 0 over 1. That is also clear because you just multiply it by 3. Yeah. So now we want to say that every element is equal to this thing. So now let's say A over 3 power n be an element of S3 inverse Z mod 15. And we will say that this is equal to one of these guys. Yeah. So A is an element of Z mod 15. Yeah. So yeah. So which one will we get? So yeah. So one has to do something. So. Yeah, so what do we do? So some maybe GCD of A and 3 power n is something one has to. Okay. So what do I have to do? So what will 1 by 9 equal to? Let's just think about this. So 1 by 9 is going to be
4 by 1.
This is going to be 4 by 1?
Yes, sir.
Okay.
Sir, I think we should look at 3 power n residues modulo 5.
Modulo 5,
Modulo
yeah, maybe.
4 would work.
4 will,
yeah. N modulo 4, basically.
So yeah, so we just try to, so you just try to, let's just verify this. So this is 1 minus 9 times 4 is 36 over 1 over 9. So this is, sorry, no, I want to check whether this is 0 in Z mod 15 or not. So it's class of this guy. Some 3 power something is 0 in this or not, but this is already 0. No, this is 35. Yeah, 35 times 3. Yeah, so this is 0 in Z mod 15. Because 5 already comes here, and then you 5 is a factor of 35. So you multiply by 3, then 15 will be a factor. Yeah. So what do we have to look? So 3 power n, you sort of look at it modulo 5. Yeah. So 3 power n is going to be say congruent to A mod 5 for some A. Yeah, and then and that's what you're then 1 over 3 power n is class of 1 over 3 power n is same as class of A over 1. Okay. So class of A over or class of B over 3 power n is just going to be class of AB over 1. Okay, where A is this number A, which is congruent to A mod 5. Okay. Say that again.
Shouldn't it be A inverse, sir?
Yes, sir. A should be in the denominator.
3 power n
is congruent to A inverse mod 5, then this holds.
Yeah.
Yeah, so A should be somewhat in the denominator. So I should take what?
A by
3
3 power n. A by 3 power n equals 1 if 3 power n congruent A modulo 5.
Yeah, so what should be the numerator? Numerator should be, so A is 3 power n is say A mod m, then you just take its inverse in 5. Is there a formula for that? There is no formula for that, but so it should be A inverse in Z mod 5, yeah. So as you can see, it already is getting messier, where then it would be okay. So maybe I should take, so let me just write it more correctly. So since 3 is co-prime to 5, there exists, let A be such that A times 3 power n is 1 mod 5. And let's just erase this to avoid confusion. Okay. AB, so given 3 power n, let A be such that A times 3 power n is 1 mod 5, then 1 over 3 power n is same as class of A over 1. Yeah, now it's okay? Yeah.
Yes, sir.
Okay. And then class of B over a general element, which will look like B over 3 power n, that will be A times class of AB over 1. Okay. So everything is going to be equal to one of these guys. Okay. So I had already sweated enough for this one. So you can see that what happens is basically 5 you get something which is so you get Z mod 5Z. Yeah. So since you have inverted 3, so you should so the way to think about it is Z mod 15Z is isomorphic to Z mod 3Z times Z mod 5Z. Yeah. And if you invert 3, then this will become sort of 0. Yeah. So because you're inverting essentially 0 of this guy. So this will vanish, and what remains is just Z mod 5Z. So if you use that logic, then that tells you that the answer for B is so this. Yeah, sorry. So if you use that that idea, then you get that the answer for this thing for B is Z. You just get Z1 over 15 because the torsion factor. So 15 becomes sort of 0. So you this factor will go away, and you'll get this thing. And if you invert everything, then of course the second factor anyway you are inverting more than S15. So you first invert S15 and then invert more if you like. Yeah? So in this C case, the only place you'll get something good is and for C you will get Q. Okay, because that's what the ring Q this ring is. Okay, does that make sense? Sorry, I sort of I didn't really think that this will be difficult, but it took a long time. Yeah, so one has to just think through what will happen. Yeah. But this, I mean, roughly this is the idea, and then to explicitly do it, it takes a little more time. Okay, so this localization, in some sense, kills the torsion part. Yeah. So this is the part to keep in mind. Okay. So maybe we didn't take a break, so I'll stop early today. And next time we will we'll use localization to define rank of a module and then move on towards structure theorem of module over PID. Okay, so are there any questions? So the class is over more or less. So if you have any questions, you can ask them.
Excuse me, sir.
Yes.
Sir, I had a question regarding that UFD and the fact that it might happen that subring of a UFD is not a UFD.
Subring of a UFD is not a UFD. Yeah, that is true.
So is there anything similar to ring extension which is a UFD or something like that? Like every ring has an extension which is a UFD or some concept like that. As long as, of course, we are assuming it's a domain.
Yeah, of course. Then it is trivial, right? You tell me. What ring extension can you take which will be a UFD and will contain it? One.
Fraction field.
S inverse R X would work.
Yeah, a fraction field. You can take a fraction field, for instance.
So but I don't want to kill many elements. The smallest one or something like that, which has the closest properties to the original ring, but yet it is still a UFD.
Yeah, so that's also true. So if you have something which is an integral domain, then I mean closest in what sense is not so is not very clear what you mean, but yeah, but you don't have to go to the fraction field. You can do it.
Yes.
In some, so you can construct, for instance, certainly a local ring. Yeah, let me not make statement in much generality, but let's say you are in a reasonable setup. Yeah, so for instance, this ring is a finitely generated algebra over a field. Yeah, or finitely generated algebra over integers or something like that. Yeah, then you can cook up a local ring. Uh, Local ring whose maximal ideal is also a maximal ideal of the original ring. So of course, if I say local ring, then you can take the fraction field again. But if I tell you maximal ideal, uh, so you localize. So some localization at a maximal ideal is again going to be UFD. So this is scaling a little less.
Yes, sir.
Yeah, and I don't think you can do better than this for finitely generated algebra over a field. But these are, I mean, of course, a bit difficult to prove at the moment. Okay, so there is something called regular local ring, and then there is a theorem which says that regular local ring is a UFD, and then there is a result which says that if you have a finitely generated algebra over a ring, which is let's say happens to be an integral domain, I mean something weaker than integral domain will also do. Then there are maximal ideals such that its localization at that maximal ideal is a regular local ring. So it follows from a bunch of results which is sort of difficult at this stage, but yeah. So these are something which the proof doesn't. It's not elementary. I mean, you can't do it using elementary methods. Okay, so it requires some more techniques from geometry and all. Okay, but I mean, the proof is algebraic. It's just that it requires a lot of work. Yeah, so you don't have the tools to prove it. Okay.
Yes, sir. Thank you, sir.
You're welcome. Any other question? Okay, so if there are no questions, then let's end the class.